Okay, today in class we reviewed average rate of change of a function. So here we have a function f of x equals x squared. And then with this type of problem, it's always going to give you an interval of x values. So this is the interval from x equals 1 to x equals 4. We're trying to figure out the average slope of x squared on this interval. So what that really is the change in rise, the change in the y values over the change in run. And this is my x2 and my x1. What I want is my y2 and my y1 so I can use this formula to figure out the average slope. So I have to use my function, right? So I plug in my x value to my function. There's my y2, 4 squared minus 1 squared. Okay, there's my change in y. I'm dividing that by my change in run, 4 minus 1. Okay, that gives me 16 minus 1 over 4 minus 1, which is 15 over 3, which tells me my average slope is 5. Okay, so that means on average, when I run by 1, I'm rising by 5 on this interval, right? So if I actually look at the graph of x squared, it's like this. Okay, it's a pretty bad parabola, but the idea is that from the interval from x equals 1, which would be like right there, to 4, 1, 2, 3, 4, right? I have this average rate of change line. So let's put a point there, okay, and then a point up here. And then what I just found was the slope of this. We call this actually a secant line, and we'll talk about that more later. But it's a line that goes through a curve at 2 different points. We call that a secant line. What this formula just did was it gave us the slope of this secant line. We found it was 5. So then we started to connect this idea of average rate of change to limits. So if we look at this picture, we have the average rate of change between the 2 black points. But if we were to draw this secant line between the blue and the black, right, here we go. Oh my gosh, that was not good. We'll try again. Okay, a little bit better. And then if we try to go through the red and the black, the line through those, right? They're pretty bad lines, but the basic idea is there, right? We see that there's this space between the straight line and the black line, and then that space is a little bit smaller between the blue line and the black line, and then even smaller between red and black, right? So what's happening is this idea is that this average rate of change line is starting to become closer to just completely overlapping the graph, right? So as the space disappears, around here, this red line is starting to look like an approximation for the black line. So this is going to start to get us into this idea of instantaneous slope. So today, to get comfortable with that, we started looking at intervals like, we'll say like 2.5 to 3, and then maybe like 2.9 to 3. Okay, and then intervals like 2.99 to 3. Okay, see how these x values are becoming really, really close together, right? Our interval is creating 2 points that are almost on top of each other. So then when we find these average rate of change, if we're still dealing with x squared, right, we do 3 squared minus 2.5 squared, and we divide that by 3 minus 2.5, right? We see what we get. And then we can do like 3 squared minus 2.9 squared over 3 minus 2.9, okay? And then we can do 3 squared minus 2.99 squared. We can do that over 3 minus 2.99. Okay, so see our y2 and our y1 and our x2 and our x1 are becoming really close together, which this is like the algebraic representation of what's happening right here. You have 2 points getting really close together. And the connection here is, if we were to say like the limit as x approaches 3 of x squared minus 9 over x minus 3, this is that same idea, right? X is going to get really close to 3, 2.5, 2.9, 2.99, right? So what we're doing when we do this limit is we're taking a limit of the average rate of change formula as 2 points become really close together. And in the next class, we'll talk more about what this is really representing.